Hello there. This is a follow-up video. In this previous video, I showed you how you can train your own compact model using the RealESRGAN code repo. And in this video, I want to show you how you can, train models of different networks than just compact, but you can train, for example, a SWIN-ER model or a HAT model or an SRFormer model. Um, and I recommend watching this video first though, so that you have the same prerequisites like CUDA installed on your system. But there is not just the real ESRGAN code base that we have here, but there are other code bases you can use for training. This one is an efficient one. More feature limited than others here, but this also made it easier for me to start with this code base, and this is why I showed this one in the previous video. You have some other code bases, so BasicSR is probably the oldest, I guess. It's the one that others forked from and added their own code. Care is the official repo for training SWIN-ER because they separated the inference code from training code. You can see that's from ETH-Zurich, and if you go to training, then you can see training code is at care here. If we go to code, then this one's also from ETH-Zurich, which can also be used to train, different networks. So this one's a trainer as well. Then we have the community ones. TraiNNer-Redux is forked from BasicSR and added additional losses, for example. Then we have a fork from that fork, which added additional, networks. And then we have sudo's trainer, which is the most feature-rich of all of these. So you can certainly try this one out as well. And the one I'm going to show is this one because that's the one I'm most familiar with. And it's the one I have used now for a while. After using RealESRGAN codebase, I went to this one to train different or newer networks, other models of these networks. So we can go to the GitHub page of this TraiNNer-redux-FJ. Hope I'm saying those names correctly. You can see it has support for different networks you can train, like OmniSR, HAT, and so forth. There are more that you can train with this. If we go to, trainer arts, then you can see you can also train, basic VSR or basic VSR++. We have the OmniSR again, the Arcan, and so forth. So you can use the same code base to train models of different networks. And so how can we use this code base? So for this, I'm going to show you how you can, clone this. You go to code, and then you copy this path here, and then we're going to open a folder. So I'll make a new one where we can then open the terminal and do a git clone with this link. So we're gonna clone this here, and we can open it, and we see we have the same, code structure that is in here. Now the folders most important for us will be the experiments folder, where we will have, the different models that we start training or experimenting with will be output here. And the options folder, where we will have the different config files for training the different networks. But first we need to install these dependencies. So I'm gonna create a new virtual environment for this, which we're gonna activate. And bin activate. Dang it. Good. So this is active now, and now we can install all the dependencies. So you can see there is a requirements text, so we can do a pip install our requirements. So we can install those dependencies that are in there. Good. Once these dependencies are installed, I can show you, you know, the config. So we go to options train, and we need to decide on the network that we will use, you know, to train this model. There are different options here. You could go with SWIN-ER or with a head model. I'm gonna use SRFormer for this example. You can see there are two example configs in here. We'll use the GAN one, make a copy, and then rename this for the model we will create. So I will do 2x. So I'll just give a model, a name for the model I want to create. You know, it will be a two times upscaling model using the dataset FHA2K, H256 compression AVC, and then SRFormer, and it's a base model, so I don't that. That's just my naming. That's just how I'm naming. You can, you know, use a simpler name, or if you're testing things out, you can also call this, you know, train test, or I don't know, whatever you feel comfortable with. So if we open this, this is like a default config file that we are provided here with this code. And then you can start, you know, adapting this config file. So the first thing in here is the name. So we'll give this model a name. Like I said, I will do a 2 times based on the FH2K dataset with AVC compression. I'm not sure how this is, you know, how we say this correctly. And then the SRFormer network. The model type, you leave it as it is. The scale, you say, you know, by what factor it will upscale. Like I said, this is a, you know, 2 times or double the input size. Then the number of GPUs you will use, you can leave that at automatic, then it will just detect your GPU, your graphics card that you have inside your computer. If you would set this to 0, it would, you know, try to use your CPU, which would be super slow. And then we have, you know, these are like the base configs. Those seem fine right now. Then we have different options here. So what those here do is you would apply an unsharpened mask. So here's the thing with all those configuration things. I'm honestly not too sure what every single one of those parameters does. And with those, I mean how the end result will look like if you've changed that parameter or if you know, set it to true or to false. And a lot of, at least for me, a lot of this was trying out. So I actually made a config where I set, you know, those two to true, because if we have, you know, a look at another config, my browser's not responding. Okay, now this. If we have a look at the code repo I showed in my previous video, you know, they will also have some training configs. Fine tune, train from scratch. For example, this one, you can see they, for example, they had set those two to true. And so what I, you know, what I did is I would, you know, set those two to true, then train the model for, you know, thousands of iterations, and then come back to the config, set those two to false, train again for the same amount with all the other things left the same, and then, you know, look at the outputs and see for myself what does actually change if I change those parameters, you know, and then I would see that if I, you know, if they are set to true, like the default config I'd use from RealESRGAN, then the outputs would look way sharper because it applied an unsharpened mask. So it made the output look sharper. But if I set those two to false, it would look more natural. So for me at least, it looked more truthful or more natural to the input image that I gave it. So this is just, and since then I've always used those two with false. This is just an example I want to show that at least for me, most of those config things is you know, trying out. There's nothing wrong with trying out. You know, try things out, find the best configs for your model that you are making with the data set, you know, with the purpose that you have in mind for your model. Train around with the config, let it train, check the outputs. So this one is you know, to help you see that, you know, I guess the most fun part about this is actually, you know, finding different configs that work. I will not use those. But what we have here is there are two different things we can do. The high order degradation basically means, do we want on the fly degradations applied to the data set or not? You know, if we would set this to false, then we would actually have, you know, an input and an output folder where we have, just kidding, two input folders, I mean, where we would have the HR input, so this one, or ground truth, high resolution or ground truth. This would be the, you know, the images in the highest possible quality we were able to acquire them. And then we would have the low resolution input, and this would be the images in the form that we want the model to learn, basically. So these are, for example, made smaller, so half the size. If we are doing a 2x model, these would be half the size of those. They would have, you know, degradations applied probably. I can show that. I'll show that after this section. So what we are saying here is we want, you know, different degradations. For example, you know, noise added or compression added during the training process. So we only give one input folder of images of the, you know, best quality we were able to acquire them. And then during training, the training code will automatically, you know, for each image, add some noise, add some, you know, JPEG compression, and add some blurriness. So the model will also deblur, which is not bad. Deblurring, at least a little bit deblurring is always good, because downsampling algorithms, you know, if you make the images smaller, it can apply a little bit of blur, let's say it like this. And you can see there are some values in here. What this simply means is that this is a range. So you won't train, you know, this model won't be trained to only handle, you know, JPEG images that were saved with the exact quality of 95, but it will, you know, take a random number, so to say, from this range, and then apply it to one image, and the next image it will take a different number, or maybe the same, but most unlikely, but it will always choose, you know, a number out of this range. So you're training the model to be able to handle, you know, a JPEG image that has been saved with 78. You know, this is for more generalization, that your model can handle more. And this is on the fly degradation. So right during training, it will make the images, you know, smaller and apply degradations to it. So your model will be able to handle this. So this is what those settings are for. They seem, I'm not sure. So let me see, this is the config. So you can see the official config for RealESRGAN was always super high. So, you know, noise of 30 added, that's a lot. I think I already showed this one in the last video, but if you take, you know, you can always test these ranges if you are unsure of how you should set these ranges here for you know, noise, then you can always, you know, go and have a look at how this would look like. So, you know, we load an image here. I'm not sure which one would be good to see the difference, but then we, you know, add noise here. And then you can see in this config it used a range between 1 and 30 for Gaussian noise. So the highest range would be 30 here. Oh, this isn't maybe not that good to show, because I don't know how this amount correlates exactly to this amount. Maybe it's not the exact same scale they use, you know, between the hood, so to say. But you can see with noise, we need to be careful, because if we, you know, you can see this would still go up to 100, but I'm very careful with adding noise, because it goes overboard super fast, I have to say. And then, you know, if you train your model to be able to handle this kind of noise, you can imagine to revert this process. It will, if you train such a model, it will destroy a lot of details in the original input image that you give it. But this was just a quick showcase of maybe a method that you can, you know, have an understanding of what could my ranges be, what do I want to train it for. For example, I'm not too much of a fan of adding noise, to be honest. But maybe it's good. It depends on the model you're trying to train. Those are those parameters, and we have the blur down here. I'm actually going to use one of my config files here. that I have made. Let me see. You can see there's a lot of different config files I've made to test things out or to try out different models. I hope this is how yours will look too. I actually, yeah, I didn't use. Let me see. Was it this one? Yes, I will use those values because I don't really want noise to be in here. Good. You can, you can try around and set those to whatever you want your model to be able to handle. You can also see, for example, in this config, they wanted to be able to handle really bad or not, just very low compressed JPEG images. And, I think, well, I don't want to go this low, to be honest. And it will retain, if those values are not too big, it won't be able to handle those degradations in a higher degree, but the details will be preserved better from your input. So, it's for you to try around, to experiment, and to decide. Then we have the ground truth size. This is super high. You can see it down here again. Normally, this is just super high. I would say try out 128 for now. Because depending on the network, it might, eat up your resources or you won't have enough resources left. And queue size, we will go with 180, which is higher again. Good. So this one is for noise and compression, and we will also have blur down here. You can see it with this blur kernel size stuff. You can see here again, they had super high blur kernel blur added. And I also went lower. I went with 12.9. This would probably be fine. I just, I like to use the configs that I had played around with so far. Sync probability. Good. So this is about the on-the-fly degradations here. These configs seem fine like this for now. So what we will also need, that you already learned in the first video about, is we need some kind of data set. And this is again the point of where I already said if you are training on the fly degradation. So this is with all these settings, with the set to true. And you can see here the type. It is a RealESRGANDataset because that's the degradation, technique we're applying here or using here basically, or strategy if that's the better word. And you will, for this one, you will only need one input folder with your dataset. And if you do, though, a paired image dataset, you will need two folders, and it's the thing I already described. I can show an example here. If we go to my datasets, for example, I have this Nomos 8K safe for work. This is this one, and you can see this is a dataset cropped into 512 by 512 pixels, which is the input images. And then I can just use that. That's what I did here. You can see I said it's this data set, and then I just applied on-the-fly degradations to make a realistic image upscale. So you can see those are also, photos. And we're gonna for here, I have also a data set that's already paired. So you can see this input folder with anime input images, a dataset by musl also, where you can see crops, also 512 by 512. Yes, from anime input frames. So those are frames from anime that are used as an input here to train an anime model. And what I did here is I created another input folder that basically contains these images, but not only are they smaller, you can see half the size to train a double up, a 2x scale model, but also I was looking if I see an example here. There's also degradation applied. So this one has video compression applied, so that we can take, the purpose of this model basically is that we can take, a frame from an anime video online that has been compressed with H.264 encoder. So, for example, this input image from Demon Slayer, you can see the compression, the heavy compression going on here. Maybe if I show it even closer. So yeah. So this model should be able to take a frame from an anime video that's been compressed, and then not only upscale it but also restore it. So this is what we're going to use for this use case, but you can go either way. It's for you to decide what you will actually do. So like I said, for this one, we're actually gonna use a paired image dataset. And so what I can do here is I can get rid of all these on-the-fly degradations and set this to false. But I want to show the on-the-fly degradations as well previously with config, so that you can, decide for yourself which route you are going. I'm just showing what I know and trying to make this a little bit more in-depth than my last video because there were some questions, but I also fear that this video will be longer. But you will get more information, so that's good. So what we will do here, or maybe I should show how I did this. Let me see. So there is a script you can use, or that I used to do this. If we go to Kim's repo, you can see the helpful scripts, and there is the DatasetDestroyer. And basically this is what I used to create that low resolution folder from the dataset. The dataset you can go, or this specific one I'm using here, you can go to the Discord from Enhance Everything, go to dataset releases, and you will find different datasets. And the one I'm using specifically here is this one, which you can download through one of those links. You can see it's 3.5 gigabytes for anime, single image super resolution, contains 2,500 images basically of 512 by 512 pixels. So some information and some showcase of those images here. So you can simply download this, and then you have the same input as I do currently. And then we can use the dataset destroyer here. You can download those files and then do the same thing again, pip install requirements -r requirements.txt in a virtual environment, and then apply, or go to the config, and then you can see my config here. that I used for JPEG, adding JPEG compression, where you can, define the output format, then what you want to be applied. So I wanted it to be compressed and downscaled, and then randomized through in which order these are applied, and then, create me a text file so I know what exactly has been done. Let me see if I actually can demonstrate this in real time. You can, of course, skip this part if you have your dataset already. So we'll take this one as an input folder, and then we'll name this output folder, test for this YouTube video. We want compression applied, and we want to downscale it to half its size so that we can do a 2x upscale. We want it randomized, yes, and we want a text file printed out as well. Let me rename this, because the text file that will be outputted will be called applied degradations.txt. I think I helped adding this functionality because I wanted to know afterwards, which image has applied what exact degradation. Then you can see the different settings. There is the blur settings, what we want to use, and the strength. Scale again, it will choose a value from in here, noise and compression. So this is already set. So normally you would find it like this if you download the config file. But for this example, I said I wanted to train a model that could specifically handle H.264 or AVC compression from anime frames. You could, of course, do also another one. And then we have this specific setting here. So this is the range in CRF format of how much compression we want it to be applied. You can ignore these ones if you do not use them. Otherwise, you can set them here. Some sort of range that you want to use this model to be able to handle. And then, let me see, I'll make it smaller. We also have the scale algorithms. So this will include down up to. I used those 4 because I just wanted to downscale to, half the size basically. And I don't use this range of values for down up. I just want it to be half the size. Good. Now for this test, we will actually set print to true. Now what this will do is it will put on the image itself what exact degradation has been applied, because this is especially useful if you use, blur and noise additionally. Should I show this real quick? If we use the blur and noise here to show it, blur and noise and compression and scale, but we only have one kind of compression currently. I'll show you. So this wouldn't make that much sense, I believe, because you're training the model to handle way too much at once. But I wanted to show though how the script works. So if I open a terminal, I need to activate this virtual environment I have here for the script, and then we do Python DatasetDestroyer. And if we start that, you can see it starts to, process all of these images or apply the degradations that we just, set in the config file. Now I'm going to, cancel this because we don't need all of the inputs. This is just a test. And you can see there should be a folder test that we said it should create. And now this is why we set, to print to true. We wouldn't do this for the final data set, but we can now go in here and we can actually see what has been applied. So you can see for this input image, the MPEG compression has been applied with this strength noise, color noise has been applied with this strength blur, isotropic blur with this strength has been applied. And you can go through each of the, images, and with this print setting on, you always see, what's going on, what did it exactly choose, and then, you can see the output image, and if you're like, well, this is way too much, then you can, then you know what has been done, and you can change the config accordingly if there's way too much blur going on or way too much noise going on. This is also useful if you set, what I also did sometimes. I'll delete this test real quick. Is we can go with just a single degradation. So we'll go compression. Yeah, I think this is good use case. So just compression. Then with compression, we only go with JPEG. So this could be a DJPEG model, right? That takes an input that's JPEG compressed and outputs an image that's, not JPEG compressed or decompressed in that sense. And then if we want to know how a specific input would look like for what range, this is also, useful for if you're doing on-the-fly degradation, we could just say, 60-60 in here. So there is no random value chosen anymore because it's just 60 for each input image. And it will output an image with only JPEG 60 compression applied, right? And so I can save this, rerun this script for just a few images, go back to the folder, and then, have a look at what does JPEG compression 60 look like exactly. And so if I'm like, yeah, my model, this doesn't look as bad as the, images I see on the internet that I download and want upscaled or something. So then you can go back and you can lower this value, What does it look like if it's 50? For example, and then, I'm just going to delete this test folder again, and then I save this config, run this script again, cancel it again, go back and look, and then be like, yeah, this is pretty bad already. Yeah, and then maybe I'm like, yeah, this is the lowest, the lowest my model should handle because this looks pretty bad already, right? And then I can go back into the script and then be like, well, and now I can add this value because I'm like, well, 50 is now the worst quality, and I know exactly what this looks like, and it should handle up to, on JPEG uncompressed images if somebody actually uses this with an image that has not been compressed. So this is how this is actually what I meant with, the configs playing around also when training the model. This is now just for the data set, but it's the exact same process I do for when I do a data set that I want to use for training a model. I'm playing around with every config, what do I want it to handle exactly? You need to know what you want your model to be able to handle. And then you need to either manually prepare the dataset like this. This is similar to the on-the-fly degradation, just I'm basically manually doing the dataset beforehand and, check visually the input images. I know exactly what it exactly looks like the input. But on-the-fly degradation will also choose, values from scales intervals that you define. So this should give also a good, view into what happens behind the scene. I'm just doing this whole process manually here. And so what I already prepared, was the compression and scale one. This one's here. I also have the file in here where you can exactly see each image name, and then the video compression I said I want to apply plus scale down, but you can see what quality was chosen for each video, which one was compressed, more and which one was compressed less, and also what downsampling algorithm has been used to, you can see to halve the image size here for this 2 times upscaling model. So that's where we are at right here. We can give this training set name H2K HVC, which is a paired image data set where I simply need, to give the correct path. I'll give the full path here, saves me from, I don't know, if I make a mistake. And then we'll use this one here. Just kidding, that's validation. I wanted this one. And then it's this one. Just so I don't forget it, I want to set this back to false because you don't want the text inside your images that you use for your dataset. Good, that was the whole config part till here already. Nice, we've already come some way and understand better of what the config does in as opposed to this video where I don't really speak about the config file, but since I think there were questions about the config file, so this is why I'm going over it a little bit more in depth here. Then we have the ground truth size again. Basically, it takes these images and then crops them a little smaller again because it will, especially okay. So it will do a crop of that size and train on crops of, in this case, 128 pixels per 128 pixels, because it loads those images, into your graphics card's storage, so to say, and will fill up your graphic card storage. So how high you can go here is depending on the RAM you have or virtual RAM you have on your graphics card. And as always, or here, higher values are better. But I think 128 is a good value to start training a model. Then we can also, flip images and rotate images during training. It will give, the network more data to. It's an augmentation technique. The network will be able to learn more. You're basically creating more images that are slightly different one of this. So we're like artificially increasing the number of different input images we actually have. Then we have, the number of workers per GPU. You can leave this. It doesn't really make much of a difference for me. To be honest, if I have 4 in here or 5 or 6, I can't really, see a difference in training speed or something when I actually change this one. So you can leave it at 6 or at 4. Maybe it's also just my system. Then we have the batch size. The batch size basically is how much, or simply said, how many different images are we looking at simultaneously, because you remember we have different levels of compression applied to these. So if we go into this, we have different levels of compression applied to these. And if it looks at one image, then, you know, in this iteration, when it looks at this image, it learns exactly this compression level, and then it looks at this and it learns exactly this compression level. So it's very simplified, but it's basically what I'm trying to say here. So we can up this. So it looks at different ones simultaneously in the same training step, so to say. And you know, if they have different values, it will generalize better, I think. Here again, the higher the batch size, the better. But it's already getting very resource intensive because we're using SRFormer. This is not a lightweight, or the architecture itself, the network will already use a lot of our resources. So if we have those crops and then we multiply those crops, it will run out of, you know, virtual RAM soon. I'm not even sure if my system can handle 4 with 128, but we'll see. Otherwise, you can decrease the ground truth size, or then in this case, if this is already at 128, I would decrease the batch size to 3 or 2 maybe. But if you can go higher batch size, then that's certainly advantageous. Yes, then we have validation is the next thing. Not sure why this is in the config. You can delete this. But here, what validation is each time. So you can see this way down here. I hope I'm not jumping around too much, and I hope the content is still understandable, and it's probably already a long video. You know, jump to the sections you need. But validation is, you can see that during training, we have a print frequency. So every 100 iterations, we will print a statement in the console. And then we have a safe checkpoint frequency. At those iterations, so every 1000 steps, it will save the current model file. So it's like a save point in a game, basically, where you're like, I want to save, this current state. So if I, die in the game or something, I can go back to this saved state. It's the same here. If something goes wrong, or you can see that after a certain step, it looks worse, for example, you could always go back to one of the saved checkpoints. And the same here with validation. We can give it a checkpoint. I like to set it the same as the checkpoint frequency, the validation frequency. And it will take one of your input images and upscale it with the current model that it's at, the current model state, basically. And then, you can say, give me these validation matrix, and then it will give you, the SSIM number, and then you can know or at least it gives you an impression if your model is still learning and improving or not. So in that sense. But I also always save the output images. And for this to work, we need something to compare it with. So we again have two input folders here. Where is it? Here. Name validation, I guess that's okay. So again, a paired image dataset where we have the image, how we would like that it looks like after upscaling. And here is the input image, how we expect input images, to be used with this model. And you can see I have a specific validation folder here with just 2 frames, I cut out from, was it a YouTube video, I believe? Which, um, yes, I think this is a frame from a YouTube video where because I wanted this model to be able to, handle YouTube, or handle if you download a video from the internet that's been compressed. So this is why I applied video compression. So this image is the one I extracted from a video that I had set to the highest quality that this video was provided with. And then I have let me see, this one, where it's the same image, but the frame I extracted was where in YouTube, I believe I set the quality to what was it, 360p, or even lower, to 80, something like that. So I extracted this, image, and it's also smaller in size. So this one is the validation input, and this one is the validation output. This is how, what my model should be able to handle, and this is how it should look like after my model processed it. So we need to input those here too. Let me just check real quick that I'm doing everything right here with a model I already trained. And if we go to options, train, this one, validation, HFL, HR, yes, was correct, the ones I said, or I showed. Good. Now, like I already said, what this does is each 1000 iterations, where it will also save a checkpoint, it will take the input image, upscale it, then compare it to the ground truth input, and then give me some metric. But I also said it should save my image as well. So I will be able to visually compare and visually see if my model is still progressing. And that is the way more important than having those metrics. You need to visually check your outputs and see if your model is still progressing or improving or not. You are the best judge of this. This is your model. You should manually, check and compare and see if you're happy with your results, or if you need, if you let this run for a while and check the saved output files and you're like, this is not going in the direction I want, then you maybe need to adopt some settings here, or change your data set up so the results you're getting is what you actually want. So after we have the validation, there is the network structure. And for this, we use the base SRFormer. So a base model, not a lightweight model. And for this, you can always go and check the official GitHub repos, because they often have their own training configs also. So we go to SRFormer, this is the one we chose, then we go to train, and you can see they have a 2x model, and you can see there is a base model and there is a lightweight model, and these will have different parameters. So if I open this 2x base model, I will simply just copy this network and then paste it in here, just to make sure we are using that official config, those parameters, because otherwise some upscaling, applications that use those things will not be able to use your model correctly. Now, in this case, it actually was the exact same config. But if you would train a lightweight model, you can see if we have a look, or maybe not copy, but just compare it real quick. You can see there's differences already in image size, window size is different. There is less, less numbers, so to say, in this array. So yeah, if I would do a lightweight model, I would basically put this also in the name of my model. And then, in the config file, I would just make a quick note for myself that this would be an SRFormer lightweight model. This is important, and I wanted to show this because I don't think the configs in here will have all of that. If I go to the folder of the one we actually just cloned with the provided ones. So if we go to like head, for example, you can see there's one head gan config with only one config setting. And so I don't know out of my head if this is a head small model or a head large model or a head medium model. So I would myself need to go to head, do the same thing, go to options, train, and then you can see here there's the hot large, the hot small, and the hot base. And so, if you were to train a hot small model, you would again, do the same thing, go in here, and then, copy and paste this part in here. 180, because you can see this is not a small one. Yes, this might be a base model. But this is why I wanted to show this. If you do your own config, be sure to, use the official parameters for the specific model size you are training. What's the difference? SRFormer lightweight will have, will be more light on resources and faster to upscale. Also, smaller models or lightweight models normally are also, in my case, faster to train. So yeah, but the bigger models will give bigger results. They will just be slower and take longer to learn or train, and will be slower to upscale images with. So there's always a trade-off, and so yeah. So next to only choosing the network, for example, head, you also need to choose will you do a base model or a small model or a large model. So you can see there's lots of decisions to make in here. Then we have the discriminator that's also being trained, that distinguishes, that basically, for example, looks at upscales and is like, how likely is this an artificial image or a real image, so to say. Yeah, there's also different discriminators. There's also multiscale or things like that. This is just the one I've been using. You can also just use this one, or you can read yourself into this topic and choose which discriminator you will be using for your model. That would probably be the best approach with all of those things, because there's so much in here just to explain. And yeah, what I did, I didn't know about all of these things. I just, as explained, trial and error. I was just trying stuff out, would change stuff up, see what's going on, would look at configs of other people that trained models, in model releases. These two are from myself, this from me, but if somebody publishes a model here, I would go and have a look if they provide the config with it, and then have a look at what they have used and if I should try one of those. So then this part is about if you will load in if you will train from scratch, or if you will load in um, an already trained model, a pre-trained model. So what this will do is it will basically, use that pre-trained model as a booster. So the longer you let it train, the more it will give outputs that you're actually your model and not what the pre-trained model already creates. So if you use a pre-train and you only train for like 5,000 iterations, then the model, in my opinion, will not be too much different from the pre-train you're already using here. So it's a good idea to actually use it because it will speed up, it will give a boost to your training at the very beginning. So what we can do here is we can load one of the official pre-trained models. So if we go to SRFormer, in this example, you can also, for example, do it with hat. But we would go check releases if there are models published here. Because, for example, in hat, nope. Some, I believe, will have it in releases. But we can just go have a look at where we can find these official pre-trained models. You can see they always, train models with some standardized data sets so they can compare their results with other networks because they have been trained on the same data sets. But we will use this one just as a pre-train because they don't always, they don't use the same degradations as we do, sometimes no degradation at all, unless they provide a real world one, but the classical one is always, those do not contain any degradations, except maybe by cubic downscaling. But we need to find, those are the results. You can see the training data sets and then compared with other networks. This is why they use the same data set, but we're still, look, here are the pre-trained models, which you can download in this case from Google Drive. So we go and look here. We can see lightweight model and base models, 2 times, 3 times, 4 times. So we're doing a 2 times base model. So we will, download this one as a pre-train. Now I actually have this one already downloaded, or not in the code base that we're doing for this video here. Experiments pre-trained models. I will put this into pre-trained models. Save it, downloaded. Good. I recognize this real quick. You can see a base model is way bigger than a lightweight model. This is what I meant also with what resources it will take up, because this one already loads a 100 megabyte model into your RAM to use it, and this one only at 20 megabytes. So this is also a point on being less resource intensive. So now we can put in here the model we actually just downloaded. YouTube test, I'm in the correct folder, experiments pre-trained model, here it is. So I copy this path with the model file, boop, like this. Good. So now we're not training from scratch, but we are using this pre-trained model file. Then we can use this one as they are because we don't have a state we're resuming from. Then we get to some training settings. These ones are fine. I actually like to use Atom W. Good. Should I do? We'll leave those like this. Then we have some losses. These are also, you know, those are configs you can try out, you know, play around with, you know, the weights and just see what it gets you. I can't really explain every single loss or what they do, but just you need to practice around with it. I want color loss though. I don't want color shift happening in my model. Let me see. This is correctly lined up here. Okay, loss 1 is the correct weight. Okay, so you can leave all of those things here the same. And then after we, you know, configured our losses, we are in the validation, the logger. I already showed this, how you can change this. Glue, interesting. Do I want to use? I normally use NCL. Good. Now we have our config file ready together with our dataset, and training could actually start now. This was basically the whole process of what we do here to configure all of this for training. And we can actually try this out now. Now there will be, I already know there will be an error thrown because the requirements file actually does not contain all the dependencies that are needed, but you'll see. So we'll go into our environment again. So all of these dependencies that we actually installed are here now. And now we can actually use a training command. So this is the Python, or you can see it here. Whoop. The Python train.py file, then options, and then we give our config file in here. This is already almost correct. So SRFormer. So you go into train, right? SRFormer, like this. And then the file I2K, we called it HVC SRFormer. So you can start after having, you know, the config and the dataset and everything ready. You can start this training command, and then you can see module not found. There is no module named anops. There's no reason to panic here because that's very simple. It's simply a module that was not in this requirements.txt file. So we simply add this one. If you have no error coming up, then that's great, and you have already everything installed and training should start for you. But we simply do a pip install inops like this. So it's installed now. We run the training command again. There is another module that we install, var scale. Then we run the training command again. Then this time we install omega conf. I'm not sure. Maybe basic SR is still missing. Or not. Oh. Well, we will know when we're finished, when there will be no error message anymore. See? Interesting. There is a different error now. I'll just install basic SR real quick, just in case this wasn't installed. So, there's a Yaml parsing error. I just want to check something real quick. Basic SR is not in here. Good. So there's a YAML parsing error. Line 19. There should be an error in here. I think it's because this one should actually be further down. Let me see in another config file here. Or then it should be on the same. Let me see. This should be all on the same. So it's fine if this is 2 more. But then all of this should be also. Let me see. So train and validation are on the same. Then we can just go 2 in for this one. Or 1 back. Yeah, so it should work now. Well, sometimes it's a little bit of pain with YAML files if the indentation is not exactly correct for all these things. Those are the same. These are the same. Good. Let's try again. Well, maybe it's not bad to have such errors during the video so you know if something's not working, what it could be. So there's actually a shape mismatch this time. Interesting. With the shape mismatch in this case will actually be with the pre-trained model. So if you load in a pre-trained model that does not have the same configuration, it will throw such a shape error. This is interesting because I used the official one, the official pre-train. Let me see. Pre-train model. This one is the official pre-train. Plus, we used the official config. Let me see. Train SRX2 from scratch. From 2, 3, 48, 5, 1, 780. Pixel shuffle. Yeah, so this one is an interesting one. I don't know why the shapes don't match. Can't be params EMA. Don't think that it's the params. Let's see how quick this is saved. Yeah, this pre-train doesn't work with our network configuration. Interesting. So I'll show you how it will look like if we train from scratch then. So yeah, this might also happen if you try to use a pre-train, or if you try to use a model from someone else, another community trained model as your pre-train, and maybe it's a small model and you're training a large model or something, there will also be a shape mismatch. So this isn't really a problem because from scratch we'll just start at 0 basically, so we just don't get the initial boost, so to say. Yes, skip connection. We don't want this in here, like this. Nice. Let us check. Wow, nice. It's starting to train. Yes, there is an error, an expected one this time. So that's good. Good that all those errors come up in this video because you will, understand and know how to resolve them if they happen to you. Also shows my real life training experience really well if I do these models, because that is exactly what I will, run into if I train models. All things like that, like nothing will just, you don't just, set the config real quick in 1 second and then you train and you're like, yeah, I have a model now. Model training is a long process, and all of this, belongs to that process. And then, next to doing all of that, you will also have it run for, 2 nights in a row or something, depending on how long you train your models. But normally my PC is running overnight and I will check the results in the morning before going to work. Let me see real quick. So yes, so what happened here is we went out of memory on our graphics card. because of the settings, right? We have a network, as you can see here, that's rather large, or a bigger network, so to say, or a resource-intensive one. Then we have the ground truth size, and with this batch size, we will run out of memory because it's loading those, patches simultaneously. So I will reduce here to batch size 2 and restart. And, then try again and see if it's still running out of memory, which means I actually need to go down to 2, unless I were to change the size or the queue size, maybe even. Let me try again. Should I change to a lightweight network? Let me just, change stuff and see if it works. No. Oh no, dang it. Do we really need to go lower on the ground truth size? Or lower on the batch size? But 2 is already low. 128 is already low. I mean... okay, it's because I'm recording and everything simultaneously. That could be it. Normally I don't need to go lower than actually this, than batch size 2 and ground size 128. Well, for the sake of this video, we will lower the ground truth size and up batch size again, because we lowered the other size, so it should still work. Let me see, go to 3 here. Still running out of memory, interesting. So it seems that we reached a point where it's not running out of VRAM anymore. That's interesting that I need to go this low, but it's probably because I'm recording simultaneously and other applications I have open in the background. But yes, it's also a good thing to show in this video, because if you run out of VRAM, because everybody has a different graphics card. Maybe yours is way more powerful than mine. I have a GTX 1660 Super in here probably currently. So you might have way more resources than me, or you might have lower resources than me. And we are training an SRFormer base model and not a lightweight model. If this were a lightweight model, it would be lighter on resources, and we would probably have been able to go with the 128. Yeah. So this is also why my first video was about training compact model, because I think compact is, for training your first model, I think compact is great, because it's light on resources and it trains super fast, and inference time, so the speed to upscale your images is also very fast. Maybe I should have shown a lightweight model in here, because this will take a while. As you can see, we are at 200 iteration steps. But I will let this train for just a little bit. And then, I won't fully train this right now, but this is to show you what it will look like with the saved checkpoints and the saved validation images. If it saves the checkpoints and validation images correctly, we will only know once we reached our first 1000 steps. And for a full training, of course, you would let this run the whole day or the whole night or the day and the night and then another night. So just however long it takes for the model to learn what the degradations that you're trying to teach it. So yeah, I will let this run for a while and then come back later. Good. So I let the model run for just a little bit, the training. There's some things I wanted to show though, some changes that I made. The first thing that I did is I was still running into memory problems, but this is why I looked at the network section a little bit closer. And I found out, if you remember, that we couldn't use the pre-trained model, the officially pre-trained model, because there was a shape mismatch. And what I saw was that if we go to their official repo, if we go here into options, train 2x upscaling model from scratch, this is the network config that we copied, right? But now the thing is, those are not the same parameters that the official pre-trained models were trained with. Because what we see here is that this holds an image size of 48, window size of 24. And now if we change to the test script, where you can see this is the test script for that official pre-trained model that we try to use, you can see here those two parameters are actually different. So those models, the official pre-trained models, were trained with an image size of 64 and a window size of 22 instead. So those are different parameters and this will not work. So this is why we were not able to use their official pre-trained models as a booster. Mind you, that's only for the base models. So the light models are consistent in the parameters they used, or the values they used for these parameters. So this problem would not have come up with the light model, but because I showed the config for a base model at the beginning. What you can do in such a case is, if you want to use the pre-train, then you could simply copy this config here that they used for the official pre-train, and then their official pre-train would work for you to use as a pre-train. I don't know, I went to this code base. If you run into something like that, you see there's some inconsistency. And what I did is I went to GitHub issues here and opened an issue where I basically just wrote that, the base models suffer from this inconsistency where the training config and the testing config actually uses different values for the parameters. And then I just pasted this in basically as an information for somebody wanting to train a model and running into shape mismatches when using the pre-trained model. So hopefully people will see this, because some people might already have problems running pre-trained models because of this. And maybe the code maintainers could add a little note here somewhere in the README, because this such an inconsistency in values can lead to problems, people using inference with such models, because of such things we might see two different base models that use either one of those two configurations, additionally to a lightweight model. But the lightweight models, they are consistent concerning what the pre-trained model used for values in those parameters and what the training configs here use. So that's not ideal, but that's something I noticed and I opened an issue about. Good. And then what I did after finding this out, and because, like I said, I was still having resource problems, I actually changed it into a light model. So I wrote in the model name, light, and then I used the light network config. If you go in here, you can copy it out from here, which will be the same as in the test scripts. And then you can see after I've changed it to light, I made a comment here about it. I could up the size again and the batch size to, this is what I meant, what I was used to. So I could up those. And then I let the training run for a little bit. And what you will get after running the training for a little bit is in the experiments folder. So what we have here is this one was the one where I, started the training process and most of the time ran into problems or errors or, CUDA out of memory errors. So I can, I can delete those. I don't need those anymore, but this is the light folder. I hope it's the correct one. So I started training again. This is a good example. So what happens here with those models? You can see this is the model name that we defined here, but you can see different folders, and some will be called archived with some number. So what happens here is because let me see, where do we have it? Here, because we don't, start the training with a specific state that we resume from, it will create a new folder. So if I run this, let me show here again. You see two archived folder and a new one. And if I run this again or start it again, you can see it will say, it's starting from epoch 0, iteration 0, because it's starting from, from nowhere. And it will create a new folder here and call the other ones archived. So those are like the previous outputs we got, and the new one, since we didn't let it run to anywhere, we won't have any outputs here. But I can still show you this one. I think was the one I let train. So if you open such a folder, and I can show you afterwards something, you will get a models folder, training states, and visualization. Models is the checkpoints that we wanted to save, like every 1000 step, like we said here. It will save model files and the training state too. And visualization is that validation that we put in there. Then this here is the training config. It will show the same as here, but there will be a timestamp when it was first run. And then this is the training log, where you will see all the outputs that you see in the terminal when you run it. If we open that models folder, then this one's empty. Maybe it was this one here. This one's empty too. Then maybe it's this one here. Yes. So this is the one that I let run for a while. So I actually could delete all the other folders. Let's do that real quick to clean it all up. You want to keep your model folders and the pre-trained models folder. You don't need to delete this one. And you can actually, rename this one again to the name. So if you open that models folder, you can see checkpoints, save points, and at what iteration point they were made, at 1000 iterations, 2000 iterations. And those are the discriminator files. So netd up till the point that you let it run. So I've let this run for 12,000 iterations. And then beneath here, you see the netg model files. And this is the one you would use actually if you were to use this model to upscale an image. So to run in inference, you would use this netg file. Next to those, we have the training states. So this one saves basically that it has run for 12,000 steps. And the validation folder contains those two input images that I had for validation with the image name here and here. And I can show, this is how you can visually see the differences. So after 1000 steps, we ran this from scratch, right? No pre-train. So you should see the difference very good at the beginning here. So after 1000 steps, it looked like this. And then you can see with every 1000 steps, it learned. For example, here the correct colors is very drastic. So you can visually see the differences very good of how the model is, learning and adapting to the content. This input image is not in the dataset that you use to train. That's important too to check results. Yeah, so you can, see the difference in for yourself to check if the model is still learning to know, to upscale, to get the colors right, to, handle the video compression in that sense. I can show you actually a better comparison where you can see it a little bit clearer. If we go to imgsli here, I input the input image and then an output image of where I had it trained to 66,000 iterations, so quite a little more. This is also Swin SRFormer Lite, where I let it train for 66,000 with the same input dataset. And what you can see here, if we zoom in a bit, for example, here the video compression details, and then you can see how the model handles those compression artifacts. So you can see it cleans that image up, so to say. It's a little bit simpler for me to sometimes spot differences between images if the model is still improving or not. If I upload images like that, for example, to this service, by creating a new album and then, adding here the input image that I actually used. Well, I would need to search for it, and then here the output image from from my model, and then you can just click create new album, and then it will actually get you to such a comparison. Yes, that's what I want to show so far. So if you don't want new folders to be created here, or if you would like to resume training, so let's say I stopped training here because well, I want to turn off my PC before going to sleep or something, or didn't want to let it train overnight. So it stopped at 12,000 iterations. So I could resume training here. And what I could do here is I actually can go to this models folder and copy the path. And then here, let me see, input, you can see the path here for the pre-trained network. So we put in here the path and the model file. So this is the 12,000 steps model file. So like this, and then we strictly load from here. And then we can do the same with the discriminator file. So it's simpler to just copy this and change this to D. And then we can do the same for the state, where we need to use the correct path, training states, and then 12,000.state, like this. So it will now actually load from the last state and should not create a new folder. We can test this in here if we want to continue from our last point. We started, and then you can see it didn't create a new folder, and here you can see it starts training from, and then you can see here the iterations 12,000. So we know that it successfully loaded our last state and continues to work on what it has already learned so far. This is just something I wanted to show real quick, how you can resume training if you're canceling it manually, or maybe something even went wrong. Um, Yes. Something else. Oh, so what can you do? What can you do after? Let's say you've trained your model and you're actually happy with it. Um, you consider it finished. You can basically take this model file, the netg, from what you're happy with, and you know I don't know, place it somewhere and then rename it and call it your model. So this would be the correct model file, and then that's the file that you could send to other people, or well, rather than sending to other people, you can also release it. So we can go to, or you can see examples. Oh yeah, here, model releases. So maybe this is a better example. This was a release I did with a base model though from SRFormer. So what I did here is I gave download links to this model file that I uploaded to Google Drive or to my GitHub repository, and then provide some information to it, like what is its purpose, how many iterations did I train, what was the batch size and the ground truth size used, you know, just information to it. And then I always like to put some examples with it. So, like this validation folder that I use some input and output images where then people can go and actually see the difference of what my model or the output my model creates with their input. This is an example input. So yeah, so providing such examples is always good. So you can release it here, and the goal here would be that people can find it here, but they could also find it on a website called openmodeldb.info, where we try to put those models that are released here also in here for a more graphical, better overview for people. It's easier accessible as a website, I guess. And you can search for a model. You can search. You can click on models. Let's see. You can also search for creators, like those are some of my models that made it onto this website, and then you can click on one of those, and then there are example files that you can slide and see the outputs. Then we have informations to this model, and then a description, and you can then download the model file directly. Something else that you might have been wondering about, let me see, since I was talking about running out of resources when doing such a base model, but here I did a base model with way higher image size that I previously showed, is because I did some part of training of this model locally on my machine, but then the other part, and that's something you can do too if you're running out of resources on your local system, or if you just have a GPU graphic card that doesn't have much VRAM. So I used Kaggle as a service, and you can see I get 30 hours of GPU usage for free each week. This always resets each week, free for everybody. And then I created a notebook in here where we might find, yes, this is the SRFormer base model here. So I can show this right away. You can see this trained for 12 hours at a time. So sessions are max or up to 12 hours. Yes, I can show the notebook. So I created the notebook here where I loaded in that input. You can see here, I put in all the commands, and you can see already the requirements plus all the other pip install commands that are missing there. And then, I let it run and test it out. I upload the config file first to, let me see, this is the training command already. Yes, so I upload my config file first to Google Drive, and then I download it here into this, you know, folder or space where this is running in, and then configure everything. And also, this one was that it, continues training from the last state. So I was also uploading first into Google Drive my netg, netd, and training state file, and then downloaded them here again. And then I ran the training command, and then I saved it by clicking save version, and then it will train for 12 hours at a piece, and I can at a time continuously training for 12 hours. So and I can shut down my PC and go to sleep and everything, and after 12 hours I can check back here. So that's useful for that. And then you can see I uploaded the data set here and then used it as an input here. And the very neat thing about this is I can set a GPU here, and here I set the GPU P100, and the P100 has more VRAM than my local graphics card. So locally here I have around 6 gigabytes, and this here has between 12 and 16 gigabytes, depending on which one of those. But it's double my resources basically. This is why on here I can, I can train my model locally for a bit, and then the finishing touches I just crank up that ground truth size, and then train it for 12 hours here additionally, and then I will release that model. Something else I wanted to show real quick too, because if you use an upscaling, application like TraiNNer, where you can, load an image, take an input image, and then, do an upscale, image upscale, and you load some PyTorch model, and then you view the result, either here or externally. So if you're experimenting with new networks, not all of them will run in such an application. So in here, if you do a hat model or a SWINER model or something like that, they all work fine here. I can show you actually. Yes, if we go to the GitHub page here, they will list all the supported networks here. Yes, so you can see, SWINER will run fine, hat will run fine, even OmniSR, which is rather new, fairly recent. This will also work in here, but some of the networks that you will be trying out might not be in here because they're pretty new or not that widely used. And in that case, you won't be able to use your model file, like since we did an SRFormer light model, and this is not listed here. This I couldn't, I can show you, I guess. If we go here, which one was it? YouTube test experiments models, and then we use the netg, but the most recent one here. Then it should not recognize this model. Yeah, you can see it, so it doesn't recognize it. But something you can do is a conversion to a model that includes all the necessary information inside that model file. I can show you an example. Because I trained this model in here, you can see the an input I want to add here, since I'm already showing this anyway, is you can see I have a lot of model file or model output folders, because I was training different models of different networks and different versions with different configurations. So don't be afraid, don't be afraid to experiment, to try around, to make different versions, to change those parameters and see, what happens and how it looks like. If we go into this folder, experiments, you can see, for example, here I have, here I was just testing out, if you look at this config file, I had all of these set to false, and then I was, using that model file and for an input and checked results, and then I did the exact same config, but I, set those two to true and trained models here, and then checked the output again. So, don't be afraid to experiment around, to, change configs, change losses, change parameters, change values, and see what gives the, the result that you are content with, that you like for your model. So, don't be afraid to change things up and to try stuff out. That's what I did. And that's how I found what I liked, like, for example, always using false with these from then on. So yeah, this is just a quick input here. But yeah, what I wanted to show is I have some conversion scripts. So you can see this SRFormer Lite to ONNX. And you can see what I'm doing here is I'm simply converting, and then I put in all the network parameters that I actually used for this model in here. And then I load a specific model file. You can see this one in here. And then I output an ONNX conversion. And the ONNX conversion file, you can see, for example, this one is an SRFormer Lite model, but this will now work with TraiNNer, even though TraiNNer doesn't support that network internally, because all the information is in that model file now, basically. So I can show this now. We can take this one and put it in here, and then it will say it's a generic model. You can start, and then there's no problem. So it doesn't show up and say that this model were not recognized or not compatible with TraiNNer, but it will actually work. And so other people can use your files to do upscales, and this is why I like to, if I show here, additionally provide such ONNX conversions. As you can see here, I did a het-l version of this series where I provide the PTH file, but also my ONNX conversion file. And then again for a het-s, where they added the small model like 2 months ago, I believe, where I also provide a PTH file and the ONNX file so that people can, use my trained models. And you can see there is a upscaled version here. So this worked. Yes, what I wanted to show is, so you can release models here, and on the website you can ask it to be put on the website. What I did here is I basically made my own GitHub repo. You can do something like that. Also, this was because I was, just pumping out models. It felt like I was just, playing around and doing different, LSTR compact, one of the first ones I ever trained, and then I started, then I made models, and then I improved upon it because I learned new things. So I did a version 2 with different conversions, and then I learned something more, and then it got even crazier with C and R, and then this is an interpolation, and then this is with no degradation, this is with JPEG compression, this is with noise and blur additionally. So I made more and more models, as you can see here. I just added model upon model and trained them and put them out. So I basically made my own repo where I, could put all the model files in, and then I would, update when I added which model, and then some visual results just as files here. Yeah, and then yeah, I have my website where I put some of my models in here, where my models can be compared against each other for specific use cases, like this anime use case, or then down here, a realistic photo. So one could visually compare and see which one of my models they would like better for their use case. And then beneath that, I also have a comparison where I upscaled this input with just all the model files I currently had on my local system, which is over 600 different, trained model files from the community and official pretrains, where I could search for one like the, official head SR model that they released, and then I could search for one of mine, like the 4x normals 8K-SC, and then we could compare. Oops, yeah, this also works. So like this, and then we can compare this trained model against, or any other community trained model against any other community trained or official model, and see, which one we like better or would work better for our use case if we had such an input image that had, similar degradations or similar content. Yes, I think that's most of what I wanted to show. I believe it's probably a very long video already, but I wanted to put this out because this server here, the Enhance Everything server, is a lot about, you can see it here, is a place for learning and collaboration. So I've just been on here learning and trying to, train models and to learn what all those things actually are, and just tried things out. And I just wanted to make this video because sometimes questions came up, and I basically wanted to share with the community at least my current understanding or process of, or what I have learned so far or understand so far. So this is why I made this video. Now, if I made errors in explanation or in things, parameter values that I set that you would not agree with, feel free to write in the YouTube comments. So there's no problem. You can correct me in the YouTube comments for other people to see and read. So I probably won't write too much in the comments itself, but other people will be able to read it and to learn from your own comments that you post. And yeah, I hope this was an interesting video. And yeah, thank you for watching.